Lesson 59, computing areas, more numerical integration on a graphing calculator. So when we talk about area in calculus, your brain is now trained to say, oh, we're going to be setting up and using integrals, right? Okay, so if you recall, the idea of an integral is it represents the area under the curve, or it finds the area under the curve. When we talk about area under the curve, we're talking about area between the curve and the x-axis. Okay, so, and that's what it talks about here. We have to first remember that the definite integral of a function is related to area. And you see this curve happening here, right? These shaded areas, I mean, if you're given the equation of this curve and asked to find the integral, it's going to find this area right here above the x-axis. It's going to find this area below the x-axis. And it's going to find this area above the x-axis. Okay? Now, when we were doing this previously, area under a curve, our graphs have not been this fancy. Okay? All of our graphs that we've worked with so far, at least if I'm recalling correctly where we're at in our curriculum, have always been pretty much above the x-axis.
There was one where there was one part above and one part below that were equal.
Okay, and that's why, okay, so we did talk about one where it was a symmetric thing, probably a sine curve or something. And the part above and the part below were equal, yes? And do you remember what happened if we just did the regular integral without doing anything special?
They gave us a 0.
They cancel each other out, right? So the idea here is that when you find an integral above the x-axis, it's going to give you a positive result. But if there's part of an integral that's below the x-axis, it's going to give us a negative result. And so when we are trying to find the area under a curve and there's multiple pieces, we have to be very careful here. If you recall when we talked, I think it was yesterday, we talked about all those integral properties and the idea that if the function is positive, so above the x-axis, then that integral is positive. If that function is negative, so right here, this part of the function that is under the x-axis, that's going to result in a negative integral. Ultimately, what this comes down to is if I just do this integral right now, I can get an answer. But if I'm specifically asked to find the area under the curve, I'm not going to get the right answer. Because what it's going to do is it's going to take the two positive sections and add those. And it's going to end up subtracting off this negative section, as opposed to adding that section in. And so what we're going to have to do is we're going to have to take this, we would take a problem like this picture and break it up into 3 integrals. Okay, we would do the integral from this first point to the second point. Okay, and we would do that integral. Then we would have to do this integral from my second to my third point. But here's the deal. If we just add that integral, we're adding a negative, which means we're going to end up subtracting off that value. In order to get it to actually add, how do you get a negative to add in? Well, and so what we basically do is we subtract a negative. So any values that are below the x-axis, we're actually going to subtract those. Because subtracting a negative value is, in terms, adding a positive then. And then we would add this integral from the third point to the fourth point there. And I just put those points in for those points, kind of points of reference of what I'm talking about there. Okay, shall we try example 1, see what happens here? Find the area between the graph of y equals sine x and the x-axis between 0 and 2 pi. The beginner calculus mistake here is to set up the integral of sine x from 0 to 2 pi and do it, and that's it. You always need to be aware of what your graph looks like and if there's any negative portions of the graph, because that means I'm going to have to set my integral up. So I would, I would always encourage you to think about the graph. This is specifically what? Sine from 0 to 2 pi? What's sine from 0 to 2 pi? There's a hill and there's a valley. And where is the break point between the hill and the valley? That break point is pi. Even though my graph looks a little awkward there, doesn't it? So we were asked to find the area, yes? Area between the graph and the curve, which means we're finding my area under the hill, and we're finding our area in the valley. What do you know about the area under the hill?
It's positive.
It's above the x-axis. It's going to be a positive value. What do you know about the area in the valley? It's under the x-axis. So just doing that integral as is going to give us a negative value. Now, if you want to be smart here, realize my picture doesn't show a symmetric figure, but this is one where if I do this on the calculator or by hand, the integral, which is what I'm going to write out, if I just do the integral from 0 to 2 pi of sine x dx, which is what I'm trying to find, right? But if I just do that integral, I'm getting 0. My area is not 0. My integral does equal 0, but my area is not 0. So this is why we're going to break it up into pieces. So what's the integral for my hill section?
2, 4. The integral of sine dx from 0 to pi.
Okay, the integral from 0 to pi of sine x dx. That finds the integral of the mound, the hill. Now, normally, we would say we're going to add the next section. But what do I know about the next section? It's going to be a negative. So to compensate for the fact that it's going to be a negative, we're actually going to subtract the next section. So any pieces that are below the x-axis, you subtract. And we're going to subtract this integral from pi to 2 pi of sine x dx. Okay? That's the official math we're doing. As we work this, nice thing is you're just integrating once. I mean, you just have to find one antiderivative is what I'm saying. So what is the integral of sine of x? I say it's either positive or negative cosine, right? You've got 50-50 shot at this point. But negative cosine, and this is where we look at the derivative of cosine would be negative sine. Since that's not a negative, we need to say negative cosine. So we're going to be doing negative cosine x evaluated from 0 to pi minus negative cosine x evaluated from pi to 2 pi. You know how to do your, this is a definite integral, right? So we're ready to plug our boundaries in. So I'm going to do the negative cosine of pi minus the negative cosine of 0. That's my first integral. Now we're subtracting. And now I'm doing the negative cosine of 2 pi minus negative cosine of pi. Obviously, the way I wrote it out, there's lots of minuses and negatives, aren't there? I'm going to clean them up in my next step. You can clean them up whenever you want. Okay. We have our cosine curve right here to help us with these values if you want. So cosine of pi. Oh, never mind. Forget what I just said. We have a sine curve there, don't we? That doesn't help me with values of cosine. Dang it. There's a cosine curve. Now I have a cosine curve. Better. Can't make myself a liar here. Or some of you guys use quadrants, right? Your quadrantial angles. I don't care what you do. Okay, what is cosine of pi? -1. The negative of -1 is going to be +1. I'm going to go ahead and say minus a negative is plus. And then I just have to do the cosine of 0, which is 1. Oh, that came up much nicer. Minus the next set. Okay, what's the cosine of 2 pi? It's 1. But the negative cosine of 2 pi is going to be -1. I'm going to go ahead and say minus a negative is plus. Cosine of pi is -1. I end up with 2 minus -2, which is 4. 4 what? This is area. So we should say, oops, units squared. I'm guessing lengths. No, I'm not. So not lengths. Packages. Oh, wow.
I don't know if it goes directly to you, but it has your name on it, so.
It is books, I'm sure. So, yep, I'll take it. It'll go to someone eventually.
Right.
Thanks.
Yeah.
I thought maybe it was Lane's coming back to get his iPad.
What's the question? Oh.
Okay.
This is not 3 different kinds of pizza.
Okay, 4 units squared. Yes? On this particular problem, it's not going to work for everything we're doing today. But on this particular problem, the other option would have been we could have done the integral from 0 to pi of sine x dx and just taken that and multiplied it by 2. I could have taken you that direction. And that's perfectly fine. So if you see something where it's symmetric and you know it's symmetric, you can take one piece and multiply it by 2, and that will be perfectly fine. That's only if you know it's symmetric. I guess I should say this is an or here. Okay. Ready for the next one? Find the area, notice the theme today, right? Of the region bounded by the graph y equals x squared minus 1 and the x-axis, but it says over the interval -2 to 2. So this means they're telling us it's not just the area between the graph and the curve. And this is more because, well, I guess last time it told us an interval 2, didn't it? Because it said 0 to 2 pi. But my recommendation, sketch a graph. Or at least visualize a graph. What do you know about x squared minus 1?
It's a parabola.
Correct? That's basic algebra 2 knowledge, in my opinion. I don't like the way I drew that. Maybe a little bit better. Okay. It is a parabola moved down 1. Now, specifically, we're going over the interval from -2 to 2. And as we do that, we need to know a little bit about this graph. This is 1 down. Where does this parabola cross the x-axis? If the vertex that's normally at 0, 0 just moves down 1, and if you remember your points on a parabola, from the vertex, the first pair go over 1, up 1. The second pair from the vertex go over 2, up 4. Does that sound a little familiar? So that means this first pair is going to be at 1 and -1. So that's not the 2, is it? So the 2 is going to be over here. And so we have to look from here to here. So when we talk about the area under the curve there, the area of the region bounded by the graph and the x-axis. What do we need to consider here?
So there's 2 positive parts and 1 negative part.
Yeah.
So we're doing a similar thing what we just did, where we have like -2 to, or -2 to -1 would be one integral, and then -1 to 1 would be another, and then 1 to 2 would be another.
That was a lot, but I think you have the idea. First of all, do you guys agree with my drawing here? Okay, my shading represents the area between the curve and the x-axis. So over here, between -1, -2, my curve is above the x-axis. So we're going between the curve and the x-axis. Here, my curve is below the x-axis. So curve to x-axis. Here, the curve is above, so above to below. Okay, and this is why you need to consider the picture, right? So officially, I tend to first write it off as, okay, it's the integral of -2 to 2 of x squared minus 1 dx. Realizing if I do that right now, I'm not going to get the right answer. Okay? We look at this. The first interval goes from -2 to -1. So I'm going to write this out, and then we can do some cleanup. -2 to -1 of x squared minus 1 dx. That is above the x-axis, so it's positive, correct? What's the next section? The next section I can do -1 to 1. Can I do all that? Okay. You can do -1 to 1 of x squared minus 1 dx. What's the catch here? It's below the x-axis, so I have to subtract that interval. And then my last piece is going to be the integral from 1 to 2 of x squared minus 1 dx. Do I add or subtract? This is above the x-axis, so we are adding. Yes?
So could we have, based on what you said, like on the last problem, could we have also done 2 times the first integral minus the second?
And notice I haven't done my math yet, so I was getting ready to do that. Did you guys catch what he said? The fact that if you look, the section from -1 to -2 and 1 to 2, are those symmetric pieces? Yes, those are symmetric pieces. And so since those are symmetric pieces, they're going to have the same value. which means if they have that same value, we can say 2 times one of them. Now, if we're going to say 2 times one of them, does it matter which we use? I like your way of thinking. You guys see what he's saying? If it doesn't matter whether we use the one from -2 to -1 or 1 to 2, we all do better plugging in positives than negatives. So what I would change this to mean is we're going to do 2 times the integral from 1 to 2 of x squared minus 1 dx. And then we still have to have minus the integral from -1 to 1. And it's all about doing the calculations. I'm giving you lots of practice of doing the math here, right? This is a very basic non-calculator problem. Okay? We haven't needed a calculator at all. So, okay, I'm going to keep the 2 out front. The integral of x squared. Yeah. 1/3 x to the third. Or you can say x to the third divided by 3 if that's your preference. Minus the integral of 1, which would be 1x, evaluated from 1 to 2. Minus, hey, what's the nice news here? Integral of x squared, didn't we already do that? 1/3 x cubed minus x, this time it's evaluated from -1 to 1. Okay? And so do all the plugging in. 2 times, let's see, plugging in 2 first of all. And that's going to be 8/3 minus 2, because 2 to the third is 8 divided by 3, so 8/3 minus 2. And then I'm going to subtract. Notice I'm putting this in parentheses. Now I'm going to plug in 1. 1 to the third times 1/3 is 1/3 minus x, so minus 1. That's my first plug-in. I didn't do any actual math there yet, but I'm just doing my plug-in. And then minus, I'm going to go ahead and plug in the next one. First of all, I'm plugging in 1. 1 to the third times 1/3, so 1/3 minus 1. Ending the parentheses there. Now I'm subtracting. I'm putting parentheses, and now I'm plugging in -1. So that's going to be -1/3 minus -1. So I'm going to say plus 1. This is where it gets tedious, right? Don't make the mistakes. I don't know. What are you guys doing here? I'm trying to decide what you guys are going to do, and I don't know. Did you guys make everything thirds? So if we look... 8/3 minus 2. So my brain says then 8/3 minus 6/3, which is 2/3. Maybe I'll just say minus 1/3 minus 1. So 1/3 minus 3/3 is -2/3. 2/3 plus 2/3 is going to be 4/3. Don't forget, though, that it is 2 times 4/3. What is 2 times 4/3? Or maybe I'll just write it like this. 2 times 4/3. Okay. Minus 1/3 minus 1 is going to be 1/3 minus 3/3, -2/3. And then negative 1/3 plus 3/3 is going to be 2/3. So negative 2/3 minus 2/3 is negative 4/3. But officially it's minus negative 4/3. So I'm going to say 8/3 plus 4/3 is 12/3. And 12/3 is 4 units squared again. Good news is, if you want to, you can check this on your calculator, couldn't you? You can put the integrals in. Don't rely on it. Don't get out of the habit of practicing this stuff. It's not as difficult, but man, there's so many places you can make mistakes. If you haven't practiced it, you're more likely to make those mistakes. That's my suggestion. Okay? Ready for example 3? Find the area of the region completely enclosed by the graph of y equals negative x cubed minus x squared plus 2x and the x-axis. Do you know what this graph looks like?
It's a cube.
It's cubed.
It's negative, so it's reflected.
Okay, it's negative.
It's wonky, so it's got maximum.
Okay. Wonky, so it has max and min. Okay. Now, officially, if we factored this out, we could graph this by hand. That's what I'm going to tell you officially. Because if we factor out, say, a negative x here, then you're left with x squared minus x, plus x minus 2. Am I right there? And so then that's a negative x. It factors into x plus 2, x minus 1. And the reason I say we could do this, we could graph this by hand, is because those are your zeros, right? You have your zeros of x equals 0, 1, and negative 2. I mean, for the process of this problem, do you really have to graph it by hand? No. And I'm not sure they'd have you worry about something like that by hand, but it doesn't hurt for me to review it either, does it? So I know it's going to cut through 0. I know it's going to cut through 1. And I know it's going to cut through negative 2. It has those 3 zeros. That makes it wonky with a min and a max. It's a cubic. It's a reflected cubic, so its in behavior is up and down. Based on the graph on the calculator, I believe the first section is bigger. It's something like that. I'm not sure that that's very accurate, but you can graph it on the calculator and check me out. Okay? Well, Shively already has, so. Oh, you didn't? Oh, you didn't get it on the calculator? I thought maybe you had it. Okay. So, if we're trying to find the area here, how many sections do we have?
2.
Yeah, and it didn't give me boundaries here, did it? Completely enclosed by the graph and the x-axis. So there is the valley and the mountain. What do we know about the valley? It has a negative value, and the mountain is positive. So, officially, it's the integral from negative 2 to 1 of negative x cubed minus x squared plus 2x dx. But we're going to break it up, aren't we? Okay. The first integral is going to go from -2 to 0, if you will. And what has to be true of this integral that goes from -2 to 0? Yeah. Normally we say we have to subtract this one. But since it's first, I'm just going to make it a negative here. And then the next piece is from 0 to 1. It's a positive, so I'm going to add it. This is where I'm running into my factory a little bit, but that's all right. Did I work this one as is? I did. Okay, you're set to work at this point, yes? There is something we can do. Might make life a little less confusing.
Can't we do the integral factor version instead?
No, because I can't integrate the factors. And I don't know, maybe I shouldn't mention this, because I'm looking at my notes, and in my notes, I just started working it at this point. But here's the deal. I don't really like having this negative out front. I don't really like having this 0 on top. Do you remember that integral rule?
It's 0 and 0, right?
No, because that just takes us back to here.
Okay.
We don't want to go there.
You can flip it and do a negative.
Yeah. If you multiply the integral by a negative, which in this case in turn makes it a positive, the -2 and the 0 flip-flop, and then you have 0 on the bottom, which is more what we're used to. Now, am I saying you have to do that? No. If I look in my notes, that's not what I did last year. Did I not think of it? Did this kid just not want to do it? I don't know, but do you guys have a preference?
I'm all for it.
I don't know that I really care, so. I mean, in all honesty, we can work it like this just to challenge ourselves too, so. No preferences either way?
I say we put
So you flip it. So if we're going to flip this, basically we normally put a negative out front, but since the negative is out front, we can disappear that negative. And so instead of going from -2 to 0, 0 to -2. And it's still of the -x cubed minus x squared plus 2x dx. The second integral is not affected. It stays as is. And if you haven't already, we're ready to integrate. Okay. Integral of -x cubed.
Negative.
-1/4 x to the fourth. Integral of -x squared. Minus 1/3 x cubed. Integral of 2x. X squared. All evaluated from 0 to -2. Plus, set up this one the same way. -1/4 x to the fourth minus 1/3 x to the third plus x squared evaluated from 0 to 1. Okay. -2 to the fourth. It's going to be a positive, and 2 to the fourth is 16. Divided by 4 is 4. With a negative out there already is -4. Right? Minus -2 to the third is going to be -8. With a -1/3, so I'm going to say plus 8/3. And plus x squared, so plus -2 squared, so plus 4. That's plugging in the -2. And now, this is why I like it. What am I plugging in now? I'm going to subtract, and I'm plugging in 0, which is 0 minus 0 plus 0 in this case, isn't it? Do you see why I wanted the 0 on bottom there? I mean, it's zeros either way, but now plus, let's set up the next one. Negative 1/4 x to the 4th. Okay, so putting in 1. Negative 1/4 minus 1/3 plus 1. And then I'm going to subtract. Now I'm putting in 0. 0 minus 0 plus 0. Always check, though. Is it all 0? Which in this case, you're plugging in for x's. But for instance, if you're plugging into a cosine, cosine of 0 isn't 0, so you have to watch out. Let's see. I see an 8/3. And then over here, I see, what are we going to have to do? We're going to have to go 12ths in this case. Negative 3/12 minus 4/12 plus 12/12. So minus 7/12 plus 5/12. Minus 7/12 plus 12/12 is 5/12. So I believe 8/3 plus 5/12 should give me my answer. Which 8/3 is going to be 32/12, right? If I multiply by 4. So 32/12 plus 5/12 is 37/12. And your mean old teacher made us all do that by hand. But in reality, that's doable, and that's what I want you guys to know. Now, notice what the backside says, though. Calculator. Okay. It is a little extra steamy in here today, so, which I know warmth puts me to sleep. So, a couple of my boys last period said, though, no, I'm sweating. I am not falling asleep. So.
See, no, that was Doc's this morning.
Yeah.
They must have cranked the heat up last night or something.
See, my room was fine, and then all of a sudden, middle of second hour, I was like, why am I feeling kind of warm in here? So, and then third hour was really bad. This is not, I don't know. Maybe I just got used to it, but. Well, usually, Shively has a pretty cold seat back there, usually. So.
I actually took my switch off.
Okay, we can use the calculator to find areas on the graphing calculator. Simply be careful of graphs that lie both above and below the x-axis. So using a graphing calculator, approximate the area of the region completely enclosed by this graph. This graph is not graphable by hand in the specifics we need it. It's graphable by hand in general, you know the shape of it, but we need some specifics. So if you haven't already, you need to graph this one by hand. Or on the calculator. My goodness.
We get to use your hands to graph it on the calculators.
There you go. We're using our hands to graph it on the calculator.
Basically the same thing.
I was in the middle of typing in letters.
I do that all the time. I go to hit delete, and for some reason my
Yeah.
phone like autocorrects to clear. Just
You have a delete button?
text.
Yeah.
You have the same buttons everyone else does, Maddie. I'm not sure what we're exactly.
Wait.
There's been an epiphany.
You're kidding me. Okay.
You've been like,
keep going.
Okay. Your graph looks like such, yes? What areas are we focused on?
The completely enclosed ones.
Okay. We've got a hill and a valley again, right? It's the area of the region completely enclosed, so those pieces that are completely sealed off. What are we going to have to know here, folks?
The integral of the hill there and the integral of the valley.
Okay, we need the integral of the hill, the integral of the valley. The hill is going to have a positive value to it. The valley is going to have a negative value to it. So I'm going to do the integral of this hill. So of x cubed minus 7x squared plus 2x plus 5 dx. And then I'm going to subtract the integral of the valley of x cubed minus 7x squared plus 2x plus 5. What are we missing? The points. How do we find said points?
They're zeros.
They are zeros.
We have handy buttons for those.
You have handy dandy buttons. There you go. And you have to find them, guys. That's, it's calculus. I would go with 4 decimal points. You remember how this is good practice. You remember how to find your zeros, right? Okay. Yours match up with mine? Or we're still finding them, right? But the integral of my mountain is going from negative 0.6868 to 1.1062. I'm going to subtract the integral of my valley, and it's going from 1.1062 to 6.5806. Now, notice we had to use the calculator here at this point, didn't we? What should we continue doing?
Using the calculator.
Use the calculator. So this is what we're going to do, I say math 9. Do the integral on your calculator. It's a lot of typing, but that typing is still going to be quicker than doing all that math, isn't it? That's interesting. We have the equation typed in y1, don't we? Since I have the equation typed in y1, you know what I think I can do?
That, and it's a lot easier.
I can pick in y. I can put y1 in there instead of typing the equation in. We've talked about that a little bit, right? We'll see if mine works out here in a moment. I should be able to, though. And it saves me having to type the equation by just putting that y1, which I find that y1 up on my alpha menu. Regardless, there's your correct answer. So, if you type it in right, you should end up with the same answer as me. If I go AP style, minimum 3 decimal places, 129.995 units squared. And of course, this is officially an approximation because we use those rounded boundary values. So you know how to use your calculator, right? And was there anything wrong with typing that equation in both places? No. Honestly, if you don't know how to use the Y1 or you don't think about it, it's just as quick to type that in. That wasn't there weren't a bunch of fractions or anything to type in there. Okay?
Calculators.
Huh?
I love calculators.
Now, if only we'd use calculators on all of them today, right?
I love
There's a-
getting-
there's
looking back.
people that used to use